Good morning, everybody. Welcome here at the Vitrolife Group Academy studio at ASRM in Denver. We're kicking off today's program with Professor David Gardner, who is going to talk more about the recent study on iDAScore that's been performed. David, over to you.
Thank you, Jacco. There we go. So it's my pleasure to present to you today the results of a multi-center prospective randomized trial that we've just completed, looking at the evaluation of IDA compared to conventional grading. And I'm delighted to let you know that this study was actually published just a couple of months ago in Nature Medicine. And these are my co-authors. I'd particularly like to highlight the input of Peter Illingworth and Toria Hardassan. They really were the ones in charge of herding the cats and the Herculean effort of getting this across the line. It was a really phenomenal piece of work. This was a multi-center trial across the Virtus Network, the Fertility Partnership, and Livio, across 4 different countries, 14 different clinics. The trial itself was supported by Vitrolife and 3 of the authors. That would be Jorgen, Mark, and Toria at the time were all employees of Vitrolife. And my declaration is that I have received research grants from Vitrolife as well. None of the other authors have anything to declare. So let's talk about where we currently are. Conventional morphological assessment. I realized when I looked at this, it's 25 years ago in this very city here in Denver that I developed the Gardner grading system. And I want to share with you some of my thought processes that went into this, because to most people it's just a number, but to me there was a lot of thought in behind these numbers. And the other thing to remember was that this was a grading system designed to assess the embryos at one time point, and that was the morning of day 5. So that's the point. It was not accounted for day 6, this was the morning of day 5. And what we already knew, and certainly from my PhD work with Henry Lees in the UK, was that the metabolic activity of a blastocyst is related to its viability. Now, we've gone on to prove that in the human in 2 successive studies. But when you look at the expansion of a blastocyst at a set time, the degree of expansion is therefore directly related to its metabolic activity, because to perform and create a blastocele is energetically very, very expensive. So that's why these numbers were important, because size does matter in this case, okay? Then, of course, for the first time, we could start to grade the embryos by their inner cell mass and trophectoderm. Up to then, we hadn't. And I had to remind myself that when we published the prospective randomized trial of the blastocyst transfer in 1998, we didn't have the grading system. And when you go to the pictures of the blastocysts, I actually wrote a description. You can see the inner cell mass at the 6 o'clock position. It's a round ball of cells. So it's really quite amazing how far we've come in just 25 years. But of course, once you've got a beautiful expanded blastocyst, you can actually then look at the inner cell mass and trophectoderm. And of course, we know the significance of those 2 tissues for implantation and fetal development. We predicted this would last 12 months and be superseded. So it's quite humbling that it's still going. But you have to understand the method behind the madness as to why this has stood the test of time, because it wasn't simply an alphanumeric system we pulled out of a hat. It was really carefully thought through. But this was a snapshot, just one Kodak moment in time. And then along came time-lapse. And with that came the capacity to look at embryos during successive periods of development, which is amazing. And like we all realized, who would have thought all the cool stuff was happening at 2 a.m. in the morning, but it did. And this is a really cool story. Like many things in IVF, or indeed science, serendipity smiles. And the story is here that Simon Cook, the scientific director in our clinic in Sydney, was giving a lecture to final year medical students. And in the audience, when Simon was showing the videos of time-lapse of the human embryo, this young man, Angus Tran, who's also a very, very good computer scientist, realized that he could work with us to develop artificial intelligence analysis. And that is how it happens. It's one of these beautiful moments in science. So that led to this publication. The AI system we developed was called Ivy. A year later, Vitrolife acquired Ivy from the Virtus Group. Once Vitrolife had Ivy, they then went on to further develop it because they had a much, much larger data set than we did. So by orders of magnitude more information, they fed into the deep learning and came up with the new system, Intelligent Data Analysis Score, IDA. So IDA was developed on an immensely large data set. And again, Jürgen, who's one of the authors, was responsible for developing it, and you can see that Angus was also part of that team who developed that. So Vitrolife could then go on and test this internally, which they did, and then they prove it in lots of clinics that they were working with to look at its robustness. And again, the beauty of it is that IDA is taking all of that information and it's looking at the fetal heart. So it's important to bear in mind when I show you the data from the trial that IDA was trained on fetal heart, not live birth. Okay. And you can see the area under the curve there. So this is the study we did, evaluating IDA selection ability, or as you can see, the visa study. And this was registered with the Australian, New Zealand authorities as a trial. So the objective of the trial was to determine non-inferiority at the 5% of deep learning using IDA. Now, bearing in mind, this was the original IDA, iDAScore 1, not the iDAScore 2 that you currently have access to, and compared it to embryologists. And they were using the Gardner grade. But we used a rigid prioritization scheme. So to make sure that everybody was determining the rank order across the 14 clinics, we came up with a rank prioritization of all the different stages and permutations from a 5BB to a 4AA. Where do they all go? And that's all in the paper. So we were pretty assured that across the 14 clinics and all the embryologists, everybody was selecting at that ranking system. As I alluded to, the primary endpoint in this was fetal heartbeat, because again, that's how IDA was trained. The entry criteria were patients under 42, and they had to have at least 2 early blastocysts on day 5. That was the entry criteria. No PGTA patients. One of the things we wanted to do as well is determine how quick it was. So we measured how long it took us to morphologically assess using standard systems, or how long it took the computer. So that was always fun. As I said, 14 different clinics from across 4 countries. And just to make it really even more challenging, we did it during a pandemic. So this is the first RCT. So this is what happened. Once patients had been deemed eligible and met the criteria, the first thing we did was assess their blastocysts using morphology. And we did that for 2 reasons. Number 1 was to make sure they were indeed eligible for the trial. And number 2, to make sure that a robust characterization of their morphology, even though it's subjective, using our prioritization scheme, had taken place. And we did that before they were randomized. So we had all that data for all the patients. The patients were then, as you can see, they were either excluded from the study or entered the study, and they were randomized by the CRF. So in the study group, for the intention to treat, we had 533 patients, and in the control group, we had 533 patients. With the discontinued intervention is shown here, so the per protocol ended up with 500 patients in the study group and 502 in the control. So that's over 1,000 patients went into this. So this to the data. Here we can show you the clinical pregnancy rate, the fetal heart rate, as determined by embryo selection of the first blastocyst, by IDA and the control group. And you can see clinically there is no difference. 47.4 for IDA selection, 48.8 for the embryologists. No difference. We then went and had a look at the time it took to do this. So what we were able to do is we grouped patients according to the number of blastocysts they had, whether it was 2 to 5, 6 to 9, or more than 10. And then we allocated the time it took either or the embryologist to assess the embryos. And this is the average. And as you can see, well, I'll tell you, it's actually about 10 times a difference. So IDA was selecting the embryos 10 times quicker than the embryologist could. Actually, it's a lot quicker than that, because that 10 times quicker meant we had to open the software, press the buttons, and do it. The actual reading and the creation of the algorithm, bang, was instantaneous. But it is quite humbling to see how quick it can be done. Now on to the non-inferiority. As you can see, when we look at the intention to treat, whether crude and adjusted, and the per protocol analysis, crude and adjusted, the non-inferiority actually breaches the 5% level. In other words, we didn't prove non-inferiority. Why was that? Why was that? So when we started to design the trial, we looked at our current pregnancy rates. And we based it around an anticipated clinical pregnancy rate of around 35%, which is what the clinics were getting. So we did the power analysis around that, and hence came up with the 992 patients we needed to recruit. So far, so good. However, our actual pregnancy rate was closer to 50%. So it's one of these things sometimes when you do a trial, you actually start to do much better than you do normally. Now here's the problem. If you want to do even a non-inferiority and your actual control is at 48%, you're going to have to recruit 7,800 patients. By the time you've even started that recruitment, the next generation of AI is going to be out. Because by the time we finish this was obsolete. So this is a really important point, and I think this was a very important study to do, but we are left thinking, how do we now move forward in evaluating artificial intelligence or anything now when really we're getting such good pregnancy rates? We have to think of other ways of determining the success or otherwise of technologies. So to summarize, this was a world-first randomized controlled trial using deep learning. That's important. IDA and its predecessor, Ivy, had no human input at all. All previous other studies had used algorithms based on annotations in which the human, the embryologist, had given information. This was a blank slate. IDA from Ivy was trained de novo on images. We only told it fetal heart, no fetal heart. The fetal heart outcome of IDA was clinically similar. It was almost identical to that, but we were not able to show inferiority, non-inferiority. But we did show that IDA was 10 times faster than us, which is interesting. And I think, again, as I said, it leaves us scratching our heads. How do we move forward in this field to evaluate new technologies? Because these trials like this are going to take so many patients, take so long, and I guarantee by the time you finish the trial, the technology will not exist anymore. It'll be the next generation. So thank you very much.
David, thank you very much for that nice presentation. Any questions from our studio audience here? No? No, David, thank you. I think it's very important what you mentioned that towards the end, the fact that we need to find alternatives of testing these kind of technologies. We can't just rely on the way we have been doing things for such a long period of time.
Yeah.
One question about being faster. Yes, 10 times faster for evaluating embryos, but what is the wider implication in the laboratory with this type of time saving?
Well, actually, we don't use IDA in Australia to make the decision. What we do, we still make our own assessment, but we have IDA to help us back up what we do. And what I mean by that is when you're in that lovely position that you've got 5 4AAs, I mean, you know, it's a nice day in the office, right? But in those days, you turn to IDA, and we let IDA then help us rank those embryos for transfer and cryo. So it's always working in the background for us. So yeah.
And I think it's important what you touch upon there, the fact that it's not there to take over the job of the embryologist. It's a a selection tool to help us in what we're doing.
Absolutely, and trust me, having been doing this for 40 odd years, I love this. I mean, it gives me greater confidence. Not that I don't doubt my ability to pick a 4AA from a 4AA, but really you can't, you know, when you've got them. And to have all that information backed up, it gives you this extra degree of confidence that that is definitely the embryo who's going to get our patients pregnant.
And it'll be definitely interesting to see where we go now with iDAScore version 2.
Yep.
You know, are we going to find new ways of evaluating that and the implementation of that in the clinic? So it'll be really interesting to follow what's happening next.
Well, absolutely, and I know that many people in this conference and yourselves, you know, thinking also, how do we assess aneuploidies? One of the things that I've talked about for a long time is that cells that are aneuploid, whether it's somatic or embryonic, experiences a phenomenon known as aneuploid stress. So if you've got an abnormal number of chromosomes, you have an altered transcriptome. If you have an altered transcriptome, you have an altered proteome, and therefore an altered physiology and metabolism. And therefore they behave differently. So this is really exciting. And I'm not saying it would supersede PGT, but I think if you can create an algorithm or use deep learning, you'll be surprised how many patients who would not have had PGT, you go, oh, wait a minute. The AI has red flagged something for us. This is really important.
No, it's complementary technology and we need to start using it together. Good. David, thank you very much.
Thank you, Jaco. Thank you.
Thanks.